Hi guys, today I'm going to show you how to use abaqus to do seismic analysis. I will use a simple column as a structure, and I will propagate the seismic ground motion to the bottom of the structure. Okay, first we create a model. We name it the file to beam seismic. Save the file beam seismic. Okay, create a part column. It's 3D model, deformable, because it's a line column. We just model it using beam element, so it's a wire. The first point 0, 0, second point 0, 10. So it's a 10-meter long column. Done. Okay. Then I use concrete material. I will just use the standard units, meter, kilogram, seconds, these units. So the commonly used density for concrete is 2,500 kilograms per cubic meter. I will just use linear elastic material for concrete. So the material Young's modulus is 3 times 10 to the power of 10 Pascal. Poisson ratio 0.3. And usually we also need to consider the damping. Here I want to use relay damping, but to correctly assign the alpha and beta values, we need to first do eigenanalysis. After we get the natural frequencies of the structure, we will calculate the alpha and beta values, and then we will go back to change these two zeros. So now we just leave it at 0. Okay, the material is defined, and then we define the cross section of the beam column. Rectangular 0.5, 0.5. So it's a 500 millimeter by 500 millimeter concrete cross section. Okay, and then we create a section, beam section, beam. Then we use this profile, concrete material. These things we just simply don't change it. Okay, create a section, and then we assign the section to this part. Do not create that, it's not needed. Okay, and we use this beam section we have just created. Okay, and then we need to assign the beam orientation, because we have just assigned the beam depth and beam width to be 0.5, 0.5. But in most cases, the beam depth and the beam width, they are different. Suppose I have a 0.3 meter width and 0.6 meter beam depth. I need to assign which direction is the 0.6 meter direction, which direction is 0.3 meter direction. The software just don't know which direction. We need to manually assign. So here, because my problem I use 0.5, 0.5, two directions, they are the same. So I don't care. But I need to assign the beam orientation. Okay, because this beam it's built on the y direction, so the two beam depths and the beam width direction is x direction and z direction. We just select one direction, now we select z direction, and we click confirm. You can see the color here now. The tangential direction is on the y direction, and the two other directions, 1, 2. So this is what we want. So we click confirm. Okay. And then we assemble. We just have one part, so it's pretty simple. Okay. And we need to do two analyses. The first one is eigenvalue analysis. Linear perturbation, frequency. I want to know the first 10 eigenvalues. The higher natural frequencies is usually not our interest in structural analysis. Okay. Now you can see eigenanalysis is here. We create another analysis, is seismic analysis. We will use dynamic implicit here. I have already downloaded the ground motion, so I know the duration of the ground motion is 24.86 seconds because my unit is seconds for time. And the incrementation, I will select fixed. The increment size for ground motion is usually 0.01 seconds, and the maximum number of increments will just increase to a very large value. Okay, other things we just leave it as default. Okay. The field output here for the seismic analysis, I only want to know the displacement, velocity, and acceleration for the stress, strain, forces, reactions. It's not my interest, so I will not check this. I will only check these parts. Okay. And the increment, because I want to know all the responses of the structure in every time step, so I will change it to 1. Every increment, it will output the result. Okay. Interaction, we don't have any, our model is pretty simple, so there's no interaction, no constraints to be applied. Load, here, in load module, first, we define the boundary conditions for the frequency analysis, eigenvalue analysis. Because our column is fixed on the ground, so I need to fix all the degree of freedoms at this bottom point. In casture, all the degree of freedoms are 0. Okay. and this boundary condition is for eigenanalysis. You can see here. Also, I need to define the boundary conditions for seismic analysis. First, I need to click here, amplitude, to load my ground motion. It's equally spaced. The interval is 0.01 second. This is my ground motion. It's in displacement. I got my ground motion and I integrate with time to convert it into velocity, and I integrate one more time to convert it into displacement. Now I copy this displacement ground motion here and OK. Now I can define the boundary conditions for seismic analysis. So seismic, actually it's a fixed boundary condition except the x direction, which is the direction I want to apply the ground motion. Displacement, rotation, select this point. Oh, sorry. Here you can see step eigenanalysis. I need to change it. I need to change it to seismic. Seismic, fixed, except x direction. Displacement. Okay, select this bottom point. Click all these directions to be 0. And this direction to be 1. And then I apply the ground motion here, which I have defined before. Okay. You can see now this boundary condition I defined for eigenanalysis, this boundary condition I defined for seismic analysis, so this is correct. Mesh. Okay. The mesh size, as you simply use 1 meter, 1 element. Okay. The mesh the part. Okay. Then we can see here, show node labels, element labels to show our node number and element number. And also we can check our element type here. You can see now we're using beam element. A linear beam element, it means this element only have 2 nodes. One node is at left, the other node is on the right. Shear flexible, it means this beam is Timoshenko beam. It considers the shear deformation of this beam. It's not Euler-Bernoulli beam. Okay, this is the beam I want. Okay. Mesh is done. Okay. I will submit this job. Submit. Monitor. Here now it's step 2. It's running the seismic analysis, the increment. Yeah, it's going pretty well. Probably it will take 2 minutes to finish this seismic analysis. Just wait a little bit. Coefficients calculation. Now the analysis is done. We can go to results to check the eigenvalues. The first two eigenvalues are the same, 305. The second eigenvalue is 11,524. So I want to use the first natural frequency and the third natural frequency to calculate our Rayleigh damping coefficient. I want to use 5% damping for both the first natural frequency and the third natural frequency. I will use here this equation. Suppose now it's 5% damping, so K1 equals 5%, 0.05 equals 2 omega 1 over 2 omega 1 alpha plus omega 1 over 2 beta. And the other one is K2 equals 5% equals 1 over 2 omega 2 alpha plus omega 2 over 2 beta. So I will solve these two equations to get alpha and beta. Okay, I get the two really damping coefficients, and then I go here, edit these two values. So my first value is 1.5028, 0.000801. So alpha is for mass proportional damping, beta is for stiffness proportional damping. To check this, which one is for mass proportional, which one is for stiffness proportional, we can go to the menu of abaqus. Here, abaqus CAE user menu, chapter 12.9.4, and you can see defining other mechanical models, define damping. Here, in alpha field, enter the value of alpha to create really mass proportional damping. Beta field, really stiffness proportional damping. So we are right. So be sure to not make this wrong, because it's very important. If you input 0.008 at the first place, 1.5028 at the second place, you will get a totally wrong result. Okay, save. Now we get the right damping, 5% structural damping. No, not structural damping, 5% material damping. And then we will run the analysis one more time. Okay. Monitor. Okay, the analysis is done. Go to the result. Check the deformed result. First, we can check the eigenmodes of the structure. Now we are in step. First step is seismic. How can we? Yeah, now I change it to eigenanalysis step, and go to the next. Eigenmodes 2, eigenmode 3, eigenmode 4, 5, 6, 7, 8, 9, 10. Yes, eigenmode looks reasonable. And then we go to seismic step. We want to know the peak displacement of the structure. So we can get a plot. We'll plot the peak nodes displacement in the x direction because we apply the ground motion in the x direction. Displacement here. Okay. Select this node. Okay. Oh, we should deactivate. Make the eigenanalysis step inactive, so we can only plot the seismic result. Okay. Plot. Yeah, this is the peak displacement of the top of the column. And we can also plot the acceleration of the top column, of the top of the column, top node, plot. Yeah, this is the acceleration response of the top of the column. We can also save it to a file. You see now, this acceleration response is this plot. We can save it to a file. Suppose I want to change it to acceleration peak acceleration.txt. Do not append. Scientific number format. And write XY data. Okay. It writes to C disk, temp folder, this file. You can see this means acceleration response. This means node number 11. The left column is the time, right column is acceleration values. Okay, this is just a simple introduction to how to do seismic analysis in abaqus, especially on structural engineering. Probably everyone needs to know how to do dynamic analysis with ground motions on structures. The model here is very simple, but it will generally tell you the procedures to do seismic analysis in abaqus. Okay, see you guys next time. Bye.